Okay, let's just dive right in with one of the biggest, most, well, mind-bending questions you can possibly ask. What is our reality actually made of? I mean, is it possible that everything you see, everything you are, is at its very core just information?
You've heard this one before, right? The idea that we're all just living inside some kind of giant computer program. A cosmic simulation run on a long string of ones and zeros. It's a really powerful thought, but what if we've got the whole thing completely backwards?
All right, so for our first section, the digital dream, let's tackle that idea head on. This notion that our entire reality is just built from simple, classical bits of information. And this quote really gets to the heart of the problem right away. The idea that reality is just simple bits has descriptive power, sure, but it has absolutely no explanatory power. See, you can use bits to describe pretty much anything, but that is a world away from being able to explain it. Here's a good way to think about it. A description? That's like the blueprint. It tells you what something is, its shape, its properties. But an explanation? Now that's the engine. That's the actual machinery that tells you why it works, how it runs. So while information theory gives us a fantastic blueprint, it doesn't give us the engine. And here's where that idea really falls apart. For one, classical bits, your basic ones and zeros, they're totally passive. They don't do anything on their own. They need an outside computer to read them, to interpret them, to give them any meaning at all. You could use bits to describe a cloud with perfect accuracy, sure, but those bits have absolutely zero power to explain the laws of physics that actually created that cloud in the first place. Okay, so our second section is called the currency of surprise. If bits aren't the fundamental stuff of reality, then what even is information? Well, to get that, we need a totally different way of thinking. In physics, information isn't stuff. It's a measure of surprise. And this is where the genius of Claude Shannon comes in. He's basically the father of information theory. His huge insight was that information isn't a thing at all. It's a precise mathematical measure of surprise. It's a number you can actually calculate. The less likely something is to happen, the more information it contains when it does. So let's make this real. Let me ask you a question. How much information, precisely, do you get when you find out the result of one roll of a fair, six-sided die? The answer is 2.585 bits. Now, notice something really important here. It's not a whole number. And that's the key. It takes exactly 2.585 bits of information to resolve the uncertainty of 6 equally likely outcomes. This is proof that we're not talking about a physical count of things. We're talking about a pure mathematical quantity that comes directly from probability. So what happens if we start to cheat a little? Imagine we have a loaded die, and it's heavily weighted to land on a 6. So rolling a 6 is super, super likely. If I roll it and it comes up 6, you're not surprised, right? You'd say, yeah, so what? It's expected, it's boring, and it contains very little information. But what if I roll that same loaded die and it comes up a 4? Whoa. Now that is a huge surprise. And because it's so surprising, that single event contains a massive amount of information. All right, our third section is reality's operating system. So if classical information is just this mathematical map, what's the actual engine? What's the territory? Well, for that, we have to go deeper. We need to peel back a layer of reality and enter the quantum realm. This is the real and, deeply strange operating system of the universe. And you know what? If you're going to play in a different ballpark, you need different equipment. The rules are different down here. So, it's time to meet the hero of our story, the qubit. A classical bit is easy, right? It's either a 0 or a 1. Simple. But a qubit, well, it can be a 0, it can be a 1, or it can be some mind-bending combination of both at the exact same time. It's not a fixed state. It's pure potential. See? Now we're talking about the engine. This isn't just a description anymore. This is the actual machinery. At this fundamental level, reality is run by these bizarre, almost magical concepts like superposition, that's being in many states at once, and entanglement, which is, it's wild. It's how reality works. But all this incredible power comes with some very strict, unbreakable rules. They're things you just can't do. They're called the no-go theorems. First, no cloning. You cannot just copy and paste an unknown quantum state. Second, no deleting. You can't just destroy quantum information. It seems to be conserved. And third, no broadcasting. You can't send one qubit to two different people. It's an inherently private, one-to-one kind of deal.
Okay, so our fourth section is measuring the quantum world. If these qubits live in this fuzzy, probabilistic world of maybe, how in the world do we measure that? How do we put a hard number on all of that uncertainty? Well, the tool for this job has a fancy name, von Neumann entropy. But you can just think of it as an uncertainty meter. It's a really clever way to put a hard number on how mixed up a quantum system is, basically how much we don't know about it. Let's go back to a coin flip. A pure state is like a coin that's already landed on the table. You look down, you see its heads, there is zero uncertainty. We know the outcome, so its entropy is zero. But a mixed state, that's the coin while it's still spinning in the air. It's a blur of heads and tails, a jumble of possibilities. It's packed with uncertainty, and so its entropy shoots way, way up. And that brings us to our final section, the ultimate calculation. Okay, so we've talked about surprise, we've talked about qubits, we've talked about uncertainty meters. But why does any of this actually matter? What's the big takeaway? This is where it all comes together. It matters because understanding this is literally the key to the future. We're talking about a future where we stop building computers that sit on top of reality and instead start computing with the fabric of reality itself. That's the whole game with quantum computing, harnessing the insane power of qubits to solve problems we can't even dream of today. And this all brings us back to that one single golden rule. Don't confuse the map with the territory. Information is the map. Just because you can draw a map of the universe using bits doesn't mean the universe is the map. Information is an absolutely essential tool, but it's not the thing itself. Which leaves us with one final, absolutely gigantic question to chew on. If the universe is a quantum computer, what problem is it solving? Think about that for a second. If the fundamental rules of reality are actually a form of computation, what is it calculating? It's the kind of thought that can really change how you look at, well, everything.